So this will take us toward reliable pumps. And this is me. My name is Larry. My last name is Backus. Everything that we own, think of your car, your computer that gives good service, maybe your watch, your cell phone. Everything that we own that is reliable and gives good service has proper design, proper application, proper operation, and proper maintenance. Think of your power tools. Think of your refrigerator and your TV. Likewise, reliable pumps also exhibit or possess proper design and application, proper operation, and proper maintenance. And everybody, that means design, operations, and maintenance, must contribute to reliability. If one of the elements is absent or incorrect, one of these four, design, application, operation, or maintenance, then the reliability chain is weak. And you can see the weak link in the chain. That's the link that's going to break. Here's an example. I was behind this car in South Africa. The engine and the chassis of this small compact car are designed for economy. This car would be adequate for a small family, mostly city driving, but it could get out onto the highway. It is not a heavy-duty work vehicle. It's not a lorry or a truck or a buggy. It's a small, what do you call it, SUV maybe? Now I'm going to show you the rest of the picture here. Just focus here on the little car as it morphs. Yeah, there we go. There's the rest of the picture. That's why we couldn't pass it. It was going too slow up the hill, going too fast down the hill. I could smell the brake shoes burning as we went down the hill. That little car is really not the right car to be pulling that kind of a caravan. Now, there's nothing wrong with the car, and there's nothing wrong with a caravan. But together, that's a bad application. And many of your pumps that you think are problematic pumps be a good pump, but it's in the wrong application. It's doing what it was not designed to do. If it's the wrong application, change it. That car will be a problematic car trying to haul a double-axle camper trailer, caravan. The big trailer, caravan, may cause this car to wreck. Even if it doesn't crash, before long the car will become a high-maintenance vehicle. This is a bad application because there's nothing wrong with the car and there's nothing wrong with the camper, the caravan. So in this particular case right here, inadequate or incorrect maintenance, inadequate or incorrect operation, inadequate or incorrect design or application leads to a weak link in the chain. Let's look at each as they relate to pumps. Here is an example of inadequate maintenance. It is a pump that is in the shop because of inadequate maintenance. Now the shop fitters install bearings. Here's a bearing. That is called the inner ring or the inner race of a ball bearing. It failed prematurely, and the question is, what is the problem? We can see the problem. The wear path, that's this darkened area right here. The wear path is not parallel to the groove, to the race. It oscillates through the raceway of the rotary ring. That bearing absorbed misalignment at the shaft and the bearing housing. So the shaft must be perfectly seated and perpendicular to the housing. And if the shaft is cocked like this, or if the housing should be cocked like that, then it's going to lead to this failure. Now this is something that happens in the shop. The mechanic who installed this bearing installed it wrong. It leads to premature failure after a few weeks or even a few days of service. And the pump is back in the shop again, being rebuilt again. Now, many plants have Vibration analysis. Raise your hand if you do vibration analysis where you work. Most places do these days. So vibration analysis will indicate the misalignment. Many places do oil analysis these days. They will send samples of the oil to the laboratory, and they will say there's copper or iron or stainless steel shards, microscopic shards in the oil. So this is why we do oil analysis, all in an effort to determine what's going wrong with the equipment. A lot of vibration analysis and a lot of oil analysis is simply monitoring the progressive degeneration of the equipment, but not doing anything to correct it. Just monitoring the progressive degeneration of the equipment. This failure will repeat itself for years, even with the most expensive vibration analyzer and with the most sophisticated oil analysis. You won't resolve this failure, you won't make it go away until the shop fitters and the shop engineers learn their contribution to reliability. Everybody must contribute to reliability. So in this particular case of the bearing, design and application and operation is good. The weak link in this chain is maintenance. Something is going on in the maintenance shop that's causing this bearing to be installed misaligned to the housing. This means the shop engineer should be on top of the fitters. If you've got numerous tables in the shop where the equipment is being repaired, and the shop engineer ought to constantly be walking around the tables and talking to the mechanics, the fitters. Now, the fitter ought to be asking questions of the shop engineer. What I find is that many shop engineers will go into the heated and the air-conditioned office and leave the mechanics out there in the weather, in the heat of the summer and the cold of the winter, doing their job, and the shop engineer and the shop mechanics never even coincide. They don't even meet. They don't even cross paths. Now that's a shame. This is a failure in leadership. Here's an example of bad or inadequate operation. The operators start, stop, and control the process pumps. Let's look at some pumps. These are parallel pumps, meaning they are two pumps side by side. Now, alternating pumps cannot run in parallel. Parallel pumps can alternate or run together, but alternating pumps cannot run in parallel. These are parallel pumps. Both pumps are turned off. You're going to start these pumps. So the process engineer says to the operator, he says, I want you to start those two pumps. Which pump do you start first? The operator should start the weak pump first. Well, you say, wait a minute, those are identical pumps. They both have the same horsepower, the same kilowatt motor, the same pump, the same, came down the assembly line together, the same impeller, the same shaft, same bearings. There's one number different in the serial number. They were bought together. One serial number ends in 6, the other serial number ends in 7. Other than that, they're identical pumps. Now, one pump will likely be the dominant pump, the other pump will be the weaker of the two pumps. You would perform right there on the spot. Don't go get your calculator, and don't go get the mathematical formula, and don't go get the amp meter. You would simply turn both pumps on against a shut valve for no more than 15 or 20 seconds. And the pump that exhibits the highest pressure on that valve, on the pressure gauge at the discharge of the pump, that is your dominant pump, and the other pump is a weak pump. Why is it important to start the weaker pump first? Now, we'll identify this as the weak pump. We'll identify this one right here as the dominant or the stronger of the two pumps. So let's say that we're going to start the dominant pump first, which is wrong. We should start the weaker pump first, but we're going to start the dominant pump first. So we bring in the liquid here. What happens if we start the dominant pump first? We bring in the liquid here, bring the liquid through this elbow right here, bring it into the pump and through the pump and through here, and we come right to here. But something else happens if you start the dominant pump first. Let's go back to where we were here. This is where we ended it here. Let's bring it down through here, bring it over to here, bring it down to here, and slam into that check valve right there. Now when the liquid can go no more in this direction, the liquid is pushed out here. Does that make sense? Now my dominant pump is holding that check valve shut. Now what is a check valve? A check valve permits flow in only one direction. So my dominant pump is holding that check valve shut, and this pump is starved on the suction side, and the output is likely to be reduced by the same percentage. So what is the weaker pump really going to contribute to my process? Absolutely nothing. So after this pump deadheads for 3 or 4 weeks, the seals and the bearings will fail from vibrations and distortion, and this pump becomes a high maintenance pump. And then somebody says, send those mechanics to a pump rebuild class so that they'll learn how to rebuild their pumps properly. The weaker pump can deadhead against the check valve right there, held closed by the dominant pump. Now this is operation and leadership, especially if the process engineer told the operator to start the wrong pump. Inadequate design. The engineers and the inspectors are responsible for correct pipe design. Now, this pump, this is the motor, the coupling, this is the pump, here's the pipe leading to this pump, this is your suction pipe, that's the discharge pipe. This pump vibrates, it eats bearings, you know, and it goes to the shop frequently. What is the problem? Now, we're looking at the problem here. Does anybody see the problem here? See, the process engineers thought they had a bearing problem. What's the problem with this pump? It's looking at you. We're looking at the problem. This is your big problem right here. You do not put an elbow, especially a right elbow, on the suction nozzle of a split case pump or any other pump. So the suction elbow is the problem. Now there's a couple of other problems. I'll just point them out to you. The last pipe support is back over here, okay? There really should be one about here. So that's your last pipe support, and this is the wrong valve. So it's got a couple of problems, but the biggie is this thing right here. Why? Well, as the liquid comes into the pump suction nozzle, a little bit of the liquid can come through the inside diameter of this elbow, come around over to here and feed this eye of the impeller down inside the pump. But most of the liquid is going to slam into the back side of the elbow and come over here and feed this eye of the impeller. So the suction elbow loads one eye of the impeller with excess velocity head. That means velocity energy. Whenever I say the word head, you can think energy. If I walk into this wall and bump this wall like that, I hit the wall with a certain amount of energy. But if I get back over there and I run into the wall, I'm going to hit the wall with more energy. And that's velocity head. Okay? So we're overloading one eye of the impeller with excess velocity head. Now these pumps are axially stable. The bearings here and here are for radial control only. Now, watch my arm as though it's a pump shaft. And the shaft rotates. If the shaft moves in this plane like this is called radial play or radial movement. If the shaft moves in this plane, this is called axial movement. So these pumps are said to be axially stable. These bearings are for radial control only. The entire shaft assembly is loaded in the opposite direction because of excess velocity head. Now, as the shaft assembly shifts, then these mechanical seal faces will open and leak and spew onto the bearings. And these seal faces over here, because the shaft is moving against those seal faces, they're going to crush, grind, and break. And then this eye of the impeller is starved of energy and it goes into cavitation. And this becomes a high maintenance pump. I want everybody in this room to think about the pumps where you work. And then the question would be, do you have elbows on the suction nozzles of your pumps? I'll just leave that for you to think about. You'll also note that those are also the same pumps that are problematic pumps. These are the pumps that have mysterious failures, bearings and seals. Somebody will designate these pumps as the bad actor pumps or the problematic pumps. But nobody has latched onto the fact that the piping is wrong. The pipe leading to the pump is inadequate. So a young mechanic, now let's consider the other side of the coin. A young mechanic says to himself, I'm going to cut this weld right here. I'm going to cut this weld right here. You can see the weld. And I'm going to take this length of pipe and I'm going to extend it way out to here. So I'm going to add 3 more meters of pipe over here, then go into the elbow, and then with 3 more meters of pipe lead straight into the pump. Now that would fix it. Why doesn't the engineer order to fix that? What's the pipe inspector doing? He's been in the plant for 20 years. Everyone must contribute to reliability. It is impossible to assign 6 or a dozen young engineers to be the reliability team, give them each a vibration meter, and then expect them to bring about a significant improvement in the pumps in a refinery or a power plant or a chemical process plant. This is going to take us toward reliable pumps. This will be a guide to stop rebuilding pumps.